So, we will start discussing something called converging diverging nozzle. In the converging nozzle, we have seen that it is impossible to get a supersonic flow at the exit because there is no diverging part. So, now what we will do is we will add a diverging part to a converging nozzle and see what happens. Okay. So, this is a nozzle which is typically used in high speed flows where you need supersonic velocities, for example in a rocket nozzle or in a supersonic aircraft. Or typically called as CD nozzle. Okay. So, what we have is a converging section, and then we have a diverging section. So, this is typically called as your throat. This is A1 and this is your exit. So, this need not be straight line, it can be any form. So, it is just that this is a function of x where this is my x. So, it can be of any shape. Okay. As long as it is 1D, quasi 1D, our analysis would be true with isentropic assumption. So, again we assume no losses, no Q, no shaft work. So, it is isentropic flow and quasi 1D. Within these two assumptions, we are going to analyze the flow as we have done before. Okay. So, there is a P0 that is coming in, there is a PB that is coming in, the PB back pressure that is existing outside the exit of the nozzle. So, what we have seen is depending on some conditions where the P here and P0 decides the choking condition or the Mach number at the exit of the converging nozzle, which is here the throat area. So, once you have that particular condition decided, so if the Mach number here at the throat is 1, then you are going to have a supersonic flow provided you have enough pressure ratio. That is what we are going to see, on what conditions you are going to have a pressure ratio here, or you are going to have a whether you are going to have a supersonic flow here or a subsonic flow in the diverging section. Okay. So, m equals 1 means the Mach number equals 1 here. After this, the flow can decelerate or accelerate depending on the pressure ratio. So, we will see what is it. So, if I write the equation for A by A star, which I will write it down here, 1 by m 1 plus gamma minus 1 by 2 m square divided by 2 plus gamma plus 1 by 2 whole to the power gamma plus 1 by 2 gamma minus 1. Okay. And this plot also has a curve of this form, A by A star. Okay. So, this is the A by A star, which depends only on your Mach number. Now, A star is the condition when your Mach number is the condition when the Mach number is 1. Now, we have suppose we have Mach number at the throat as 1, if m at throat is 1, then your A throat can be considered as your A star. Okay. Or I can replace this equation by A at the exit divided by A at the throat equals, since we have already assumed isentropic flow, my A star is going to be constant. So, the moment I assume isentropic flow, I write three things. What are they? T0 equals constant, P0 equals constant, and A star equals constant. Okay. Under the assumption of isentropic flow with no heat, no shaft work, no entropy change. So, under this assumption, these three are always true, which we will assume it here. So, your A star, when Mach number at the throat is 1, then we can call A throat as my A star, which means I can write AE by A throat as AE by A star, which now only depends on your Mach number. Or to put it the other way around, gamma plus 1 by 2 gamma plus 1. Or to put the other way around, the Mach number at the exit is going to depend only on this ratio. Okay. So, your Mach number at the exit depends only on this ratio, AE by A throat. A star if your Mach number at the throat is 1. Or if the throat is choked. So, if the throat is choked, I can make this statement: M exit depends only on my area ratio, which is A exit by A star. So, when I say area ratio for a CD nozzle, it always means A at the exit divided by A throat. Okay. So, for a given area ratio, if the flow is choked, my exit Mach number depends only on my AE by. And once you have this exit Mach number, my P exit by P0, T exit by T0, everything now depends on your ME, which is dependent on area ratio. So, area ratio decides all these factors if the flow is choked. Okay. Now, we are going to see what is this condition. Like what we have done before, we will try to see when you change your PB, what happens for a given area ratio. Okay. So, I have a throat and there is a area exit, there is a P0 which is constant, there is a P exit, there is a PB. PB is my back pressure. Like what we have done in our converging nozzle, what we will do here is we will keep this constant for a given nozzle. I will decrease my P0, PB, back pressure. Okay. So, I draw a line. Again, we are going to consider only flow inside. Outside, what happens is not being considered at present, which we will discuss it in the following lectures after discussing normal shocks and oblique shocks. So, when P0 equals my PB, there is no flow. So, I have a fabricated nozzle in my hand, there is no flow, there is no pressure difference. Let us take P by P0. Now, I decrease my PB to some value such that the flow at the throat is not choked. So, I would have a subsonic flow in the converging nozzle. The flow has not reached M equals 1. and now the subsonic flow faces a diffuser. So, it again decreases my velocity. So, here in this region dA is negative, in this region your dA is positive. Now, I have a subsonic flow. So, dA is negative. So, my velocity increases. Once it reaches your throat condition, it faces a diverging section. So, velocity decreases. So, this would go to some value like this. Okay. So, this is some PB which is does not create the chocked condition. So, if I decrease my PB again, I may get m equals 1 at the throat. Okay. Now, once I get m equals 1 at the throat, I have this condition. It can either decelerate or accelerate. Okay. So, I for a given, let us say for a given A by A star. Now, since it is already chalked, I can call this as my A star and this as my A. So, for this AE by, for given AE by A throat, I have two values of Mach number. Okay. So, this is my subsonic Mach number, this is my supersonic Mach number. Okay. So, one of these values would happen here. So, either the flow will decelerate or the flow will accelerate. So, this is my P by P0 by P0 is kept constant. So, P0 by PB by P0 at say, so if this is line 1, this is 1, PB by P0 at 2, this is PB by P0 at 3. Okay. So, this is chalked. So, this value here P throat by P0 is less than your P star by P0. So, that the converging nozzle is now chalked. So, this flow is chalked. So, we say the throat is chalked. Once the throat is chalked, I have these two conditions for the given area ratio. Mach number 1 is subsonic, Mach number 2 is supersonic. So, I have two solutions, something that happens here, either subsonic or supersonic. Okay. Now, whether it is subsonic or supersonic, let us take M2, depends entirely on your pressure ratio. And this is the isentropic solution. So, this is the isentropic curve, and what I am describing here is the isentropic solution. Okay. So, in between what happens is a non-isentropic solution, which we will discuss it later. For the time being, once the flow has chalked, it can have two solutions, subsonic and supersonic, as I have described here in this particular plot, where A by A star gives you two solutions. That precisely that thing happens here. It can have two solutions, either the flow will accelerate or the flow will decelerate, depends on your back pressure. Okay. This Mach number again M1 or M2 entirely depend on the area ratio, which we had just now seen. Okay. But which solution will be picked decided by your pressure ratio. Now, we will go further and draw the Mach number variation. Okay, I will draw it a bit. So, for the case, well, let us put line 1, line 2 and line 3. Okay. So, remember here between 0 and 2 we have infinite number of isentropic solution, but once the flow is just chalked, it has only 2 isentropic solutions. One is this, one is the subsonic case. Okay. In between you have non-isentropic solution, which is typically the shocks and other things, which again as I told you we will discuss it later. Okay, so now we will try to see how the Mach number variation is. So, let us start from Mach number equals 0 line. Let me draw it slightly lower. M equals 0. So, let us draw for the case 1. So, the flow is accelerating, but it has not reached Mach number 1 at the throat. So, let the throat condition is here. So, the flow is accelerating and it has not reached 1, and then the flow see a diverging section. So, it decelerates. So, the Mach number reduces. Okay. And depending on your pressure ratio you would have your exit Mach number, okay, because the flow is not now chalked. So, your area ratio will not decide your exit Mach number, only your pressure ratio will decide your Mach number. So, this Mach number is decided by your pressure ratio Pb by P0. Now, you have a condition where the throat is m equals 1. So, you have some value here which is 1. So, this is your axis. So, the flow because of that some pressure ratio, your flow increases to Mach number 1 at the throat. The flow is chalked. Once it is chalked, it has 2 solutions, one is supersonic, one is subsonic, decided by your area ratio. So, it goes here or it goes to some value here. So, this is my curve 1, this is my curve 2, this is my curve 3. Okay. These 2 values, once the flow is chalked at the throat, these 2 values M3 and M2 will be decided by your area ratio, and the which one is picked is decided by your pressure ratio. So, for any pressure ratio between these 2, you have a non-isentropic solution, or any pressure ratio after this is also going to have a non-isentropic solution outside the nozzle. So, that is my next curve, curve 4. So, I have reduced my Pb further than this. Okay. So, here what happens at Mach number 1, the throat condition is still Mach number 1. So, it can go to subsonic flow if the pressure ratio is this, but now we have reduced it much further. So, the pressure ratio would be this line plus, so it would take the same line as this and then do something at the exit to reach the reduced Mach number pressure, reduced Pb. Okay. So, like that it will go through the same curve here up to this point, and then it do something outside the nozzle to do get a different curve. So, I repeat, what the process we have done is we have a constant we have a nozzle with some area ratio, and Pb is kept, P0 is kept constant. I am decreasing my Pb. So, when I decrease my Pb, I start getting a flow. So, as I slowly decrease my Pb, there is some point at which you will get m equals 1 at the throat. The exit Mach number it is again a subsonic flow, because it has not reached a pressure ratio where you can get a supersonic flow. So, so you have a point at P2. Now, if you increase it further down, you would get a supersonic flow which is an isentropic solution. In between this these two isentropic solution, you have infinite number of non-isentropic solutions. So, any pressure Pb between, say for example, Pb2 and Pb3, you are going to have a non-isentropic solution. Okay. So, this is for Pb1, this is Pb2, this is Pb3. Pressures between Pb2 and Pb3 are non-isentropic solution inside the nozzle. After Pb3, if I reduce back pressure smaller than Pb3, I am going to have no change inside the nozzle, but outside there will be some changes which we will discuss it after discussing shocks. So, the exit Mach number is going to be what you have decided by your area ratio. Okay. So, this Pb2 we call it as first critical pressure or first critical point, okay, and 3 we call it as the third critical point. In between comes your second critical point, which again we will defer it to discuss sometime after discussing normal shocks. So, I repeat, I will draw a new curve, I will repeat the whole process again. So, I am going to repeat whatever we had done now. P0 is kept constant, Pb is decreasing, I have a P exit. When P0 is same as Pb, no change, there is no flow. Now, I decrease Pb to some value which would give me a subsonic flow at the exit. So, this is Pb0, this is Pb1, Pb1 gives me a subsonic value at the throat. If I decrease further my Pb, I will reach m equals 1 at the throat, but Pb is not enough reduced to get a supersonic flow at the exit. So, this value is isentropic flow. So, this increases the velocity and then suddenly it decreases because the flow is facing a diffuser side. Now, if I decrease Pb further than Pb2, this is 1, this is 2. If I decrease my Pb further, I will have other solutions here which are non-isentropic, but once you reach Pb3, so I am decreasing. So, I decrease Pb to some small value. So, I have a solution here which is non-isentropic, then I have another solution here. So, there are infinite number of non-isentropic solutions here between Pb2 and Pb3, but once the pressure is reduced to Pb3, I would have a supersonic solution which is isentropic. Okay. So, your P, this is your P exit, this would be your P exit, this will also be your P exit, and this will also be your P exit. In between, your P exit is not equal to Pb in this region where you have non-isentropic flow, okay, which we will discuss it later. Now, if I reduce my Pb further, there is nothing that would change inside the nozzle, but outside the flow will do something to reduce your P exit to Pb. Here again your Pb is not equal to P exit. So, these lines are the isentropic solutions. In between here 1, 0 and 2 you have infinite isentropic solutions. This region you have infinite non-isentropic solution, and this is the line that demarcates between the isentropic and accordingly your Mach number also changes. Okay. Now, we will do it with the small example. The same thing what we have discussed now, we will do it with a small value, so that this would become clear. So, I have a P0, some P0 of so let us take 100 kilopascal, and I have decided my A exit by area to be 2.5. Okay. Okay. Assume flow is choked, meaning M at the throat is 1, Mach number at the throat is 1, my A throat equals A star. So, my area exit by, I can write it as AE by A throat equals 2.5, which means my area is 2.5 times of your A throat. Okay. So, your area A exit is 2.5 times of what you have at the throat. Again, I assume isentropic flow and other things, your A star is going to be same as here throughout the flow. Now, we have said once the flow is choked, this will decide your exit Mach number. Okay. So, you look at the table for gamma equals 1.4, look at the isentropic table, AE by A star equals 2.5 gives me 2 Mach numbers M1, M2. So, M1 is going to be 2.5, M2 is going to be 2.44, M1 is going to be okay. So, I have two isentropic solutions for this particular area ratio if the flow is choked. Okay. Now, which one will this flow takes? So, let us look at the pressure ratio. Since it is isentropic flow, we know P0 is constant. So, M1 0.24 gives me a P by P0 of 0.24 gives me a P0 of 0.961, 2.44 gives me a P by P0 of 1.4. So, I will make sure this is for gamma 1.4. Okay. So, this is for gamma 1.4. Okay. So, in the problem what we have defined, we have kept our P0 to be 100 kilopascal and we have an area ratio and we are assuming flow to be choked. Now, these two solutions give me P1 to be 96.1 kilopascal and P2 to be 6.4 kilopascal. So, if my this is P1. So, if my PB1 96.1 kilopascal, which means I have a P0 here, PB here. If PB is P0 is 100 kilopascal, PB1 is 96 kilopascal, I am going to get a subsonic flow, which is this curve. Oh no, this curve, which is your isentropic flow, this curve. So PB equals 96 kilopascal. If it is reduced further to 6.4 kilopascal, I am going to get a supersonic flow. Okay. So once the flow is chalked, area ratio decides everything. That is the main point from this discussion. So once the flow is chalked, area ratio decides everything, and between these two solutions, the pressure ratio decides itself to get your this. Okay. And for any other pressure ratio, area ratio, any other pressure ratio less than PB2, so greater than PB2, that is inside in the subsonic side, you can have any number of solution depending on your area ratio and the mass flow rate. So once the flow is chalked, so again chalked. So at the throat, AT equals AT equals A star. So for a fixed AE by AT, this quantity is also the maximum that it can go through. Okay. So the mass flow rate that is going through the nozzle once it is chalked is the maximum it can take. The maximum flow rate then comes from this particular condition, which depends only on P0 and T0. So unless you change T0 and P0, your mass flow rate is not going to change. Okay. So whatever you do, your throat condition is same. Your M at throat is 1. So your AE by A star is going to decide what is the Mach number at the exit, which would decide which would be one of these two curves, and given those conditions you can find out the other quantities, and your M star is the mass flow rate is again decided by your stagnation quantities, which is not decided by your area ratio. Okay. So this is the maximum mass flow rate it can go through. So we will do numerical problems related to whatever we have discussed now, maybe in next class or a class after that. So what we have seen today is CD nozzle, the importance of area ratio, which is the area at the exit divided by area at the throat, thus decides the entire flow regimes, isentropic flow regimes in CD nozzle. And we have also seen that the two solutions, isentropic solutions, are possible once the flow is chalked inside the nozzle. Again, outside the nozzle we are not discussed anything, we will do that few classes later. So the importance is the area ratio, CD nozzle area ratio decides everything. Okay. Thank you.